Okay, so let's go over what we had done in last lecture in the canonical ensemble. Now, remember, we started with the microcanonical ensemble, where the energy was fixed. And we assumed that in all the microstates are equally probable. That gave us a picture. Now, in the canonical ensemble, what we will be studying, or will be systems where, let's say, I have a system that exchanges energy with the environment. The number of particles will be fixed, the volume will be fixed, but it is allowed to exchange energy. But of course, then this approach we will use for systems in contact with a heat reservoir that's at a given temperature. For example, in our everyday life, most of the systems that we see are in interaction with the atmosphere. The atmosphere has more or less a constant temperature for a short enough time intervals. So your body, this keychain, the tables, they are systems in contact with a heat reservoir, which is the atmosphere, and can exchange energy with the atmosphere. So since we already know what to do for an isolated system, one approach to such systems would be to look at the system plus the environment. The environment meaning everything that can exchange energy with my system, so that the whole system will be an isolated system, and I can use the microcanonical ensemble. So then I ask the question, what is the probability that my system will be in some microstate that we called R? And we looked at that probability, and it turned out that that probability was just an exponential. It depends only on the energy. Also remember our discussion on the Liouville theorem. The density in phase space, we expect it to be a constant or a linear function of energy or a linear function of the number of particles. So you see here that this probability density is actually just, if you take the logarithm, it's just some constant times of linear energy times some constant. And then we said, okay, we have the probability, there's that normalization constant, normalization factor in the denominator, but then we saw that when we calculated the average energy of the system, we saw that we can actually express the average energy of the system by just in terms of that normalization factor, which we call the partition function of the system. So if you know the partition function as a function of the temperature, or the beta in this case, the inverse temperature, just differentiating with respect to beta gave us the energy. If you know the partition function, let's say, as a function of volume, that's the next step. Then we looked at the general definition of the entropy. Remember, in our microcanonical ensemble also we said that we could identify the entropy as the logarithm of the probability, the expectation value of the logarithm of the probability with a minus sign. And in this case, we know the probability. We just did the algebra, and we had seen that logarithm of z is just minus beta times the free energy of the system. So we started with the partition function. We said that, okay, if we know the partition function, we can calculate all the other properties, like the energy, the average energy. Well, if you know the average energy, if you identify the entropy in that form, the logarithm of z just turned out to be the free energy. And also, if you remember our discussions on the thermodynamics in our first week, if you know the free energy of the system as one of the thermodynamic potentials, by just taking its suitable derivatives, you know everything about the system. So this is another way of studying a system that is in contact with a heat bath. So calculate the partition function. It will be a sum over all the microstates available to the system. And then take the logarithm of that sum, and you have the free energy. So any questions up to here? Let's look at a couple of more things. So we know the probabilities, PR. Let's calculate the average pressure. So for a given microstate, let's say the pressure is PR. Sorry for my notation. Let me change this slightly. Let me call the pressure by this curly P, because I don't want to get confused with the probability of the R microstate. Let's say that PR is the pressure that the system exerts when it's in the Rth microstate. Then the pressure that we actually measure will be just the average of this PR. Well, how can we calculate these averages? Well, it's nothing but the sum overall microstates of the system, the pressure in that microstate, multiplied by the probability of that microstate. The pressure of a given system is nothing but the derivative of its energy with respect to volume. This ER here is the energy of the Rth microstate. It's not the internal energy of my system. It's not U, it's the energy of one particular microstate. And multiplied with PR. I know what PR is. That is e to the power minus beta ER divided by Z, the partition function. Well, this I can write as sum over R. Let me move the 1 over Z out. Sum over all the microstates of the derivative of this beta function. Remember, when I'm taking the derivative with respect to V of that exponential, I'm only differentiating ER. I'm treating beta as constant. But beta is temperature. So that basically tells me that this derivative with respect to V is the derivative with respect to V at constant temperature. So again, this is nothing but minus derivative with respect to V of t of the, no, there's no minus sign here. This is plus derivative with respect to V of logarithm of Z. Remember that derivative with respect to V I can take out of the summation, because summation doesn't involve the volume. So I end up having the derivative of logarithm of Z. This is at constant temperature. But the pressure, if I know the free energy, I can write the pressure as the derivative of the free energy with respect to temperature. Now, with respect to volume at constant temperature with a minus sign. The left-hand side is my thermodynamic property. By the way, I forgot a factor. I have to divide by beta. Yes, if I take the derivative with respect to volume of that exponent, I will get a minus beta times the derivative of the energy. That is why I have to divide by beta. So here I have K times T. 1 over beta is just K times T. Or let me just write it 1 over beta. And again, these two derivatives have to be equal at all temperatures. And in fact, volumes. Again, I obtain logarithm of Z is equal to minus beta times F. You see, on one hand, I know plus some constant, of course. You see, even if I don't use the definition of the entropy, I had already seen that writing the energy of my system as the derivative of the logarithm of the Z, I know that Z, logarithm of Z is minus beta F times some function of volume. Now this derivation tells me that F, logarithm of Z, should be minus beta times F plus some function of temperature only. But that additive constant should be a function of only the temperature or only the velocity. For it to be at most the temperature of at most the velocity, for both of these to be true, that should be just a constant. And that constant is fixed by the third law. If you calculate the entropy, that constant has to be 0. So again, we see this relationship between the partition function and the free energy. And of course, once we have the free energy, we have all the other thermodynamic properties.
What is the reason that it's just a function of temperature rather than other parameters?
You see, this is a differential equation. It's a first order differential equation in V. And I can solve that differential equation by saying that logarithm of z divided by beta has to be equal to minus f. Remember, if I add a constant to this equality, constant with respect to v, my differential equation is still satisfied. Since I'm taking the derivative with respect to v. If I add some function of t over here, it doesn't change the v derivative. So that is why logarithm of z and beta times f should be minus the free, can at most differ by a function of t. We had also derived a similar relation for the time derivative. And that told us that logarithm of z over beta has to be, let me see, not beta over here, has to be equal, logarithm of z had to be minus f times some other function of v. So, you see, the only way that these two equations are both satisfied is if g and f, they are both constants, in fact 0.
Same constant.
Yeah, oh, sorry, this is, I have beta over here. That has to be a constant. Now let's look at another thing. And we have been calculating the averages. We are doing statistics. I mean, since the first lecture we started discussing statistical physics, I have been claiming that the fluctuations will be negligible. The probability of deviating from, let's say, this equation this is essentially sorry. U is the average energy. But if I measure the energy of my system, what is the probability that it will deviate from this average energy? Yes, my system will be exchanging energy with the environment. So its energy will not be fixed. It will change. There will be fluctuations in the energy. If I measure it now, I might find one energy. If I measure in 5 minutes, I might find a different energy. In fact, if you look at the PR, you see all microstates are possible. In fact, it looks as if microstates with low energy are more probable. They are more probable with microstates with higher energy. In fact, the ground state is seems to be the most probable microstate. AR will be 0. That's the largest PR you have. As we increase the energy, the probability of a given microstate decreases. But when I make an observation, the energy I will observe will not be the ground state energy. It will fluctuate. How much will it fluctuate? Well, that is usually given by the variance of such probability distributions. Let's say delta E, the fluctuation in E squared, I will define it as E minus U squared average. Or you can also write this as the average of E squared minus the average of E, the average itself squared. Now let's see what this is. Let me look at the average of E squared. This is equal to sum over all microstates, the energy of that microstate squared times the probability of that microstate. sum over r of ER squared e to power minus beta ER over Z squared. No, over Z, sorry. This is 1 over Z, derivative with respect to beta, twice derivative with respect to beta of e to power minus beta ER. Well, I can, if I take the derivative with respect to beta of that exponent, once I get a minus ER, the second derivative will give me a minus ER all squared. Well, the derivative with respect to beta is actually inside that summation, but since beta is independent of the microstate, I can just take it out. But that is nothing but my partition function. Well, let me do a small trick here. Between those two derivatives with respect to beta, I will put a z and also 1 over z. Now, the reason is this is equal to 1 over z del by del beta of z times derivative with respect to beta of logarithm of z. Remember, what I will eventually use is that this is nothing but minus u. I'm kind of trying to relate it to the energy. This will be equal to 1 over z, derivative of z with respect to beta. I'm just taking the derivative of this z times minus u plus 1 over z times z times the second derivative with respect to beta of the logarithm of z. Again, this is minus u. So E squared average, remember I'm calculating E squared average, will be equal to u squared plus the second derivative of beta with respect to logarithm of z. Remember, I'm looking at the fluctuations on E squared. This will be E squared minus the average of E squared, which will be E squared minus u squared. But now from this equation, I know that that difference is just the second derivative with respect to beta of logarithm of z. I'm not writing it explicitly, but I'm taking all these derivatives in this discussion at constant v. Delta E squared will be derivative with respect to beta of derivative of logarithm of z with respect to beta. But again, that derivative of logarithm of z with respect to beta is just minus u. So the fluctuation in the energy squared is actually minus the derivative of the energy of my system with respect to beta at constant volume. Now remember, beta is 1 over kT. So I can convert that derivative with respect to beta to derivative with respect to t. So this will be equal to kT squared, derivative of u with respect to t at constant volume. So this is the fluctuation in the energy of my system, the fluctuation squared. Now, remember the first law of thermodynamics, which states that du is equal to dq minus dw. This is 0 at constant v. So du by dt at constant volume is actually del Q by del T at constant volume. But this is nothing but the heat capacity at constant volume. So if you like, you can express the fluctuation as K times T squared times the heat capacity at constant volume. You see, one of my claims when we were discussing thermodynamics was you can express everything, all the thermodynamic properties, in terms of just a couple of derivatives. Derivatives of the equation of state, the specific heats, that's enough. We have the Maxwell's relations to relate one derivative to the other one. It's just playing around, and we will end up being able to express almost everything in terms of just a bunch of derivatives of other thermodynamic properties. So what does this tell me? I mean, I don't even need to realize that the fluctuation is proportional to the specific heat. You see, T is an intensive property. It doesn't change with the size of the system. So as T. So as, I mean, the T in the derivative. But U is an extensive property, which means that U should scale as the number of particles in my system. If I double the number of particles in my system, U is doubled. But this tells me that the fluctuations in my system, fluctuation squared, should increase with the number of particles. Yeah, this seems to be exactly the opposite of what I was claiming. You see, the fluctuations are increasing, but keep in mind that we are not actually looking at the absolute fluctuation. We will be able to measure only relative fluctuations. Now, delta E over E. This will be square root of n. This is my delta E. E scales as n. 1 over square root of n. Well, what does this tell me? Well, if you take n to be something of the order of 10 to the power 23, delta E over E would be 10 to the power minus 10. You see, if you have a fluctuating system, the importance of this delta E is that, I mean, whenever you measure E, let's say, you won't be measuring an exact energy. It will fluctuate. The probability that the energy that you actually measure will be within this delta E is given by around 68%. The probability that the energy you measure will be within twice this delta E, I think it was something around 90%. And the probability that the energy you measure will be within 3 delta E, for those doing particle physics, these are just 1 sigma, 2 sigma, and 3 sigma, it is more than 99%. So with more than 99% of the probability, when you measure an energy, yes, it will be fluctuating, but the energy you measure will be within an E plus minus 3 delta E range. Let's put some numbers. Let's say that the energy of your system is 1 joule. Well, the corresponding delta E, well, let's say 10 joules. Delta E will be 10 to the power minus 9 joules. 1 part in 1 billion. You will get fluctuations, but the fluctuations you will get will be 1 part in 1 billion. Your device will not be able to measure the energy with such a precision. You won't see, with your measuring devices, you won't be able to observe any fluctuation in the energy. So even though we have a system that can exchange energy with the environment, the energy will be fixed for all practical purposes. But this also tells us that for such a system, well, I can use microcanonical ensemble. I can use canonical ensemble or microcanonical ensemble. I should get exactly the same answer, because there will be no, although the system in principle can fluctuate in energy, it will not fluctuate. It is as if the system is isolated. Of course, you have to identify U with average E. Sorry. E with average E. Because in microcanonical ensemble we have a fixed energy, here we have an average energy. In fact, this is the reason why in my notations I sometimes use U, sometimes use energy. It doesn't make any difference. It doesn't fluctuate. In fact, this is what we will observe in general. In a given system, the fluctuations in any quantity, the relative fluctuation will be of the order of 1 over square root of n. Now, if you would plot, let's say E over E max. There's no E max. E over U. This is E over U is equal to 1. What is the probability that the system will have a given energy? For a small number of particles, what this means is that square root of n will be not so large, 1 over square root of n will be not so small, so delta E over E will be somewhat large. So this probability will look something like this. This is for small n. But if you go to larger and larger n values, this probability distribution will become like this, because delta E is nothing but this width. This is my delta E. It will become narrower and narrower. Even effectively, it becomes a Dirac delta. So although we will be always looking at probabilities, I can definitely say that the energy of the system is such and such, and all my measurements will measure that given energy. But I would like to emphasize once more, it is valid for very large values of n number of particles. For thermodynamic for macroscopic systems, n will be huge, but if you try to apply this to systems of, let's say, 100 particles, the probability distribution will be large, the fluctuation will be large, so you have to take that into account. Okay, so let's do an example, a short example of this approach. You see, we will solve the ideal gas over and over using different approaches. Again, let's look at this ideal gas within this canonical ensemble. Now, what's an ideal gas? It's basically a gas where we ignore all the interactions among the particles making my system. If I ignore all the interactions making my system, the energy of my system will be sum of the energies of each one of those particles from 1 to n. So this is the sum over the energy. EI will, of course, depend on the position and coordinates. In general, it will depend on the position of the energy of the ith particle will depend on the energy and position of the ith particle only. And in fact, if we are looking at identical particles, the dependence on position and momentum will be identical for all of those particles. We had already seen that if we are able to calculate the partition function, we obtain the free energy. If we have the free energy, we are done. The sum of all the partition function is the sum over all microstates of e to power minus beta times sum over I of EI. Well, the sum over microstates The microstates of my system are determined by the position and momentum of all my particles. In the microcanonical ensemble, we had already seen that we can sum over the microstates by integrating over all those. But we have to divide by h cubed. Now we also counted these microstates, summed over the microstates in the microcanonical ensemble of e to power minus beta of EI. But you see, the integral over the position and momentum of one particle is independent of the integral over the position and momentum of the other particle. So this is, let me write this exponent in a slightly different form. This is the product of e to power minus beta EI over I. Product of exponentials is nothing but the exponential of the sum. So that is what I use to convert this exponent to a product of exponents. But then my partition function is nothing but, well, let me also introduce the 1 over n factorial, the Gibbs correction factor already over here. This is 1 over n factorial d cubed pi d cubed qi over h cubed e to power minus beta ei. Now I have the integral over the momentum and coordinates of all those particles, but I can write that 6n dimensional integral in terms of the product of n 6-dimensional integrals, because the momentum and coordinate of each particle is separate. The energy is just the sum of the energies of each one of the particles independent of the others. So I have this relationship. Just pick any one of those i's. But then that integral is just the partition function of a single particle. Yes, this is the partition function of n particles. I'm integrating over the position and momentum of all n particles and dividing by n factorial. If you look at this integral over here, it's just like the same thing as summation over all the microstates of my system, but this time, since I have one pi, one qi, is sum over the microstates of a single particle only, which tells me that Zn is just 1 over n factorial z to the power z1 to the power n. Again, I repeat, and z1 here is the partition function I would obtain for a single particle. Yes, I still don't know what these EIs are. What is the expression of the energy of my particle? Let me use one more information, that EI, remember this is E of, it depends on the momentum and coordinates. If there are no external potentials, the energy will not depend on the position. So this will be actually just a function of pi. Energy only depends on the position. If that is the case, energy depends only on the momentum. If this is the case, then I can evaluate the qi integral. That's the integral over the position of my particle. My particle is within some volume v. That integral will just give me v. So Z1 will be actually v over h cubed times d cubed p e to power minus beta energy as a function of p. This is my Z1 now, the partition function of a single particle. Well, that tells me that Zn is 1 over n factorial h to the power 3n v to the n d cubed p e to power minus beta e of p. This is my Zn. Now that integral, let me leave it as it is for the time being. That integral depends only on the temperature. There's no position dependence there, so it doesn't depend on the volume of my system. So what do I know? I know that Zn is 1 over n factorial h to the power 3n v to the power n times some function of temperature. Let me take the logarithm to obtain the free energy. Minus beta f minus beta times the free energy is nothing but logarithm of Zn, which is n times logarithm of v. This is v to the power n. Minus n logarithm of n plus n. This is 1 over the logarithm of 1 over n factorial. I use the Stirling's approximation. Then I have plus the logarithm of f of t divided by h to the power 3n. Sorry, here there is an nth power. There is an n over there. So what does this tell me? The free energy is minus nkt logarithm of v plus some function of t and n. Now I can calculate, for example, the pressure will be the minus derivative of the free energy with respect to volume at constant n and t. But if I keep t and n constant, that f tilde function, whatever that is, it will be a constant, its derivative will be 0. So this is just nkt over v, or pv is equal to nkt. And we again recover the ideal gas equation. And keep in mind that here, it is in this derivation, I don't know how the energy depends on the momentum of the particle. I didn't use that. For example, here you can consider a gas of non-relativistic particles, which will have E of p will be p squared over 2m. A gas of relativistically moving particles, like the photons, for example. In that case, energy will be equal to p times c. Whatever the system is, PV is equal to nkt. It might be, I don't know, xenon gas, one of the noble gases of single atoms. It can be a carbon dioxide gas, or it can be a more complicated molecule with complicated internal dynamics. It doesn't change the equation of state. As long as I can make this approximation, this is an approximation. It ignores any interaction between the particles. That is the first approximation. The second one assumption in my system is this one. As long as I make these two assumptions about my system, I have the ideal gas equation of state. And also keep in mind that if you remember how we had obtained this in the microcanonical ensemble, we had to deal with all these 6 n-dimensional integrals, we had to calculate the 6 n-dimensional solid angle expression, etc. Well, this is the only thing I need to do is evaluate the 6-dimensional integral. 3 of them were already trivial. It just gave me the V. Well, let's be more thorough. So f of t, so this is my z of t, z of n. Let's look at the non-relativistic gas. E of p is just p squared over 2m. So this integral remember, p squared is px squared, py squared, pz squared. I am integrating over all px and py and pz. That is basically a 3 Gaussian integrals. Each of those Gaussian integrals will give me 2m pi kt under the square root. I have 3 of them. This is the result of that integral. So z of n, this is my f of t is then 2m pi kt to the power 3n over 2. Well, what was my free energy? This is my free energy expression. Which will be n times logarithm of v over n, the first two terms, plus n times 3 logarithm of 2m pi kt to the power 3 halves divided by h cubed. This is my minus beta f. I had some bad notation over here. F of t is this integral inside this f of t to the power n. So f of t is this is my f of t. Well, let's see what will be the entropy. F is minus n kt logarithm of v over n plus 3 over 3 n kt logarithm of 2m pi kt over h squared plus n. Entropy will be minus derivative of f with respect to t at constant temperature. Well, you see, this is also kt over here. Well, so all of those terms have one t, one overall t. So I can write that as minus f over t. This is the derivative of the t in front of all those terms. Then I have another product, another derivative of whatever is multiplying that overall t. That will be plus 3 over 2 nkt. Well, there's only an additional t dependence in that logarithm. Derivative of that logarithm of t would be 1 over t. So entropy is minus f over t plus 3 over 2 nk. Remember how we defined the free energy? That was E minus Ts, or energy is equal to free energy plus temperature times S, which is the free energy, plus if I multiply this with temperature, I will get minus F plus 3 over 2 nk, which will nkt, which will be just 3 over 2 nkt. Now, this is in fact what we had already obtained for the energy of the ideal gas. Now, let's go back over here. Let's go back to this expression, the entropy. You see, we had calculated entropy also in the microcanonical ensemble. I do advise you to go back and compare this entropy with the entropy we obtained. And you will see that we have the entropy in the microcanonical ensemble as a function of number of particles, volume, and the energy of the system. Now we have the entropy in the canonical ensemble as a function of the number of particles, volume, and the temperature of the system. You will see that these two are exactly equal if you take E is equal to 3 over 2 nkt. Well, this was in fact what I had claimed before. So macrocanonical ensemble and canonical ensemble should give me exactly the same result Because although in the canonical ensemble I allow energy fluctuations, energy will not fluctuate. It is as if it's an isolated system. If it behaves as if it's an isolated system, then I can also treat exactly the same system in the microcanonical ensemble. And if you just go back to your notes and compare the two, they will be exactly equal. Of course, if you identify the fixed energy in the microcanonical ensemble as the average energy in the canonical ensemble. You see, this is the average energy in the canonical ensemble. This is the fixed energy in the microcanonical ensemble.
This holds for ideal cases, right? Not the generalization. We are saying for those ideal cases.
You see, if you go back to our discussion about the fluctuations, this is a general argument. I don't know what that CV is. I don't know what that derivative of U with respect to T is. For different systems, it will be different. But the only thing I know, the only thing I need to know is that CV, the heat capacity, is proportional to the number of particles. So the fluctuation squared will be proportional to the number of particles, so relative fluctuations will always be roportional to 1 over square root of f. Okay, before you go for a break, let me also note one more thing. You see, on one hand, if you look at the probability expression here, I said that the system, the most probable microstate of my system is the ground state, because ER is smallest for the ground state. But on the other hand, when I look at the energy, the average energy can have any value depending on the temperature, and it is definitely not the ground state. Well, you see, the issue here is the probability of the system having energy E would be equal to sum over all microstates of sum over all microstates such that the energy of that microstate is equal to E of the probability of that microstate. You see, I have many states having the same energy E. So if I'm only looking for the probability that my system will have that energy, well, that is just the sum of the probabilities over all microstates that have that energy times the probability of each one of those microstates. But this is nothing but PR times omega of ER, because the PR is the same. And R here, I'm summing over R. Here, R is just any of the microstates in the sum. Now, PR, let me also write it explicitly, depends only on ER. So if you would plot as a function of ER, now PR drops exponentially. But if you also remember the expression of omega ER, it increases exponentially. The larger the energy of your system, there are more states having that energy. This is omega of ER. And PR times omega ER has this dependence. Okay, the ground state, among all the microstates, the ground state is the most probable microstate, but there's a single ground state. but there are billions of states having a larger energy. So although each state has a lower probability, but if I'm only measuring the energy, not the microstate, the probability that my system will have that larger energy will be larger, not because the probability of each one of those microstates is large. It's very small, but there are so many of them that at some value over here, it is maximized. You see, at very low energies, there are very few states. So the probability of you observing any one of them will be negligible. If you go to very high energies, on the other extreme, although there are a huge number of states there, the probability is so small that the enormous number of microstates cannot compensate for the smallness of the probability. Somewhere in between, it's kind of these two extremes cannot exactly cancel each other, so you have a large probability with small fluctuations. Any questions? So let's give a break here. Now in the next hour, okay, we will still continue in this canonical ensemble. But although I'm saying canonical ensemble, I didn't use any ensemble theory here. In the next hour, we will see how we can drive these results in the ensemble theory. I will just imagine these many copies of my system. And then I will again ask myself the question, what is the most probable distribution of microstates in my ensemble, or the average?